afternoon, and welcome to the OAA Conference 2021. My name is John Robus, and I'm from Exterior Technologies Group. Today, we'll be looking at a presentation on the safe use of combustible claddings in non-combustible construction. I am the principal of Exterior Technologies Group, Canada. We have offices across Canada, in Atlantic Canada to Vancouver, of course, Toronto, and the Calgary, Edmonton area. Exterior Technologies Group provides comprehensive design services for architects such as you and specification writers on your team. We help you with detailing a project and specifying the proper materials for the building envelope. The products ETG represents are alpolic materials, like aluminum composite panel, CalZip, which is the world's leading standing seam roofing system and cladding system, Epic Metals, which is a high span and long span decking system and ceiling system, Zinc, of course, that describes the zinc material itself made into various wall claddings, and Knotwood, just as the name says, not wood, it's aluminum. Alpolic is the world's leading manufacturer of metal composite materials. We're located in Europe, North America, South America, as well as Southeast Asia and Japan, as well as India. Some of the projects that we've done around Toronto, this is the quad at York University, River City Complex in downtown Toronto, a multi-unit residential complex, Ryerson University. We also do a number of schools and community centers throughout Canada. CalZip, the world's leading high-performance standing seam roofing, was introduced in Canada about 9 years ago by us and has become very successful. CalZip offers a range of roofing products as well as wall cladding products. And these are some images of the projects recently completed. Zinc is a new entrant and a new manufacturer in the world of zinc materials. Located in Oviedo, Spain, they've become now one of the leading manufacturers of zinc coils and sheets. Again, some of the images that you see are a recent project. This is a dark zinc that was used on Sherwood Community Center, another community center in Ottawa, a correctional institute for women, some other government buildings, and so on. We also did Union Station locally here in Toronto at the UPS Express. With all those cladding products, they need sometimes a subsystem, and that's what Radius Track is. Radius Track is a subsystem that achieves complex geometry. One of the most complex buildings that we've done, it's a zinc-clad building, but the shapes that you see on these photographs are achieved by that subsystem. We've also worked locally on the TTC subway line, and this is the Vaughan Metropolitan Station, and York University, and also the 407 station. They had highly complex roofs. This is another picture of the Shane Holmes YMCA at Rocky Crest in Calgary. Radius Track is also extensively used to achieve curved shapes in interior applications. The last one is Epic Metal, and Epic is a roof deck system as well as a ceiling system, which offers high acoustical values, and just some recently completed projects with that system. And of course, Knotwood is similar to longboard. Just as the name says, it's not wood, it's aluminum. We've been doing some Tim Hortons and Wendy's and KFC's, McDonald's, and a strip mall in Halifax, Nova Scotia. We also have battens with Knotwood that achieve great shading, if you like, and they're a nice visual aesthetic element. That was a short introduction to Exterior Technologies groups and some of the projects that we've done around Canada and completed around Canada. But this next slide shows you our learning objective today. We want you to really today understand the safe use and how to specify combustible wall claddings when used in non-combustible construction. Here's a look at our agenda for today. We're going to cover several subjects with regard to the building code, with regard to testing, with regard to trends in wall systems. But firstly, I want to start with why we're here. Why we're here is really the Grenfell Tower fire has been a subject in the architectural community and in the building community for a number of years now. This was a fire caused by really a perfect storm of mistakes in construction. The exterior cladding on this building was the wrong type of exterior cladding, and the insulation was polyisocyanurate, which was never tested with the type of exterior cladding in the fire. Plus, the cavity from the exterior cladding to the insulation was quite large, which allowed the fire to propagate up the building. So after seeing that slide, why use these combustible claddings? What do they offer? Well, they offer superior rigidity, superior flatness, no oil canning or distortion on the surface of those claddings. They're really construction site friendly, and they come pre-finished in a wide range of finish options, anything from a wood grain to a prismatic paint to a solid paint. And they have flexible detailing, and they're very lightweight. And most of the panel systems that you see around your cities in Ontario are fabricated locally, and they're very cost effective. So let's get into some of the types of non-combustible claddings. The types of non-combustible claddings are solid monolithic metal panels such as steel, aluminum, copper, stone, insulated metal panels with mineral wool insulation, some high density fiber cements. And I'd just like to just show you some photos and details of some of those cladding types: zinc cladding, copper, granite and limestone. You'll recognize most of this: mineral wool, IMP, terracotta. Now that I've introduced you to some types of combustible claddings, let's look at those claddings and the materials that they're made of. And let's look at the tests that are required to prove that the material is non-combustible. The first test is CAN ULC S114. It is in the National Building Code of Canada and in most provincial codes in Canada. It's a very severe test which heats the material up to about 1700 degrees Celsius, and the material has to sit in that chamber for about 20 minutes. If nothing happens to it, doesn't lose mass or doesn't catch on fire, then it's considered non-combustible. Another method in the building code so that a material can be qualified to be non-combustible, the material must be tested to CAN ULC S135. Now, this is a, if I can say, an easier test to pass. The S114 was very severe, and nothing could pass it except solid steel or solid stone, concrete, brick, and so on. But the S135 is another method which the code accepts to be considered non-combustible. So they measure the material that is going on the wall or being used as a cladding, and that material has to have a heat release less than 3 megajoules per meter squared. Now, if the material is a combination or a laminate, and it has some distinct layers like an outer skin, a middle core, and a backskin, all those three elements must be tested separately. Now, let's look at types of combustible cladding materials that are commonly used in construction here in Canada, in Toronto, in Ontario. These types of materials, you see them daily: high pressure laminates, insulated metal panels, wood exteriors like thermal wood or composite wood panels, some fiber cements, metal composite materials, and so on. Here's a phenolic panel, for example, really nice design by Perkinswell's architect. And you can see why they selected the material. A lot of materials wouldn't fit into that design. Exterior insulated finishing systems, or EFIS, are combustible with the polystyrene or polyiso type insulation. Insulated metal panels, which are used in warehouses and so on, in replacement to precast, that sometimes have a very high insulating value, but the skins are made of steel. There's a foam core of polyisocyanurate and a backskin of steel. Of course, some wood claddings that we're using now, and you as architects love wood claddings, but you have to be cognizant of the code with these claddings. And then aluminum composite materials, such as Alucobond or Renobond, the trade names, but basically a laminate material, also a bonded material with an outer skin, a middle core, and a backskin. Now, all these materials have to be tested too. So if, going back to the previous slides, if you can't pass S1 CAN ULC S135, if you cannot pass CAN ULC S114, then the code, because we have an objective-based code in Canada, allows you to be used in non-combustible construction, but another test is required, and that is the CAN ULC S134. It's a full-scale wall test for combustible claddings that are used in non-combustible construction. And in the building code, and then again, going back to those slides where for example, the code asks you to run a S135 to see if your material is non-combustible. If you release more than 3 megajoules, it directs you to this clause in the code, 3.1.5.5, for combustible components in exterior walls. And in Ontario, combustible components should not be used more than 6 stories in building height if the building is sprinklered. And that's Ontario only. In the National Building Code, you can use these combustible materials to any height, and all other provincial codes in Canada can be used to any height. And that's where this CAN ULC S134 is referenced in that section of 3.1.5.5. Here's a picture of the test. It's not a very clear picture, but we'll see the test a little bit in action later on in the presentation. But it's a very big apparatus, measuring about 3 stories high. We basically light gas burners in the apartment size area. It has a window, a large window, and that fire is allowed to propagate out the window and move up the wall. So the only way you would fail this test is if that fire burns the panels more than 5 meters beyond the window. And then the heat flux, that's the amount of heat released by the panels or the wall cladding itself, is greater than 35 kilowatts per meter squared. Then you would fail. What does that test evaluate. I just went through it, but this slide presents it again. It measures this fire spread over the exterior surface of the wall, the heat flow from the fire plenum to the exterior surface of the wall, and it measures the fire spread within the test specimen. One thing to note that there is a new version of the test, 2013. It's similar to the old 1992 version, except now the panels have to have a joint in the middle of the window opening. And Canada's test is probably one of the most severe in the world. Next, I'd like to discuss fire behavior of combustible facade claddings. Anything from phenolic to EFIS to metal composite panels. If you see that graph or chart on the right-hand side of the screen, you see high-pressure laminates at the top, and at the bottom, some fiber cement boards. So the 256 is the amount of energy that that panel or the phenolic panel is releasing. Metal composite panels are somewhere in the middle, and then you see fiber cements down at 12.8. The next slide just illustrates comparing those values of heat release in facades. Wood siding and high pressure laminates are all, 225 megajoules per meter squared. ACM and IMP type panels are in the middle. We have a new core that's used in Europe with ACM panels called A2, which has a lower value, and then fiber cements are low. So that just keep that in your mind when you're selecting these products. Now that we've learned something about fire behavior of the claddings and energy release, let's look at selecting a combustible cladding in buildings of non-combustible construction. In the design phase, you're going to go to the building code and you're going to look at the code and you're going to consider the following. You're going to look at part 3, which is the fire protection and the life safety aspect, which we discussed. We're going to look at structural design of your envelope system, the environmental separations, of course, heating and ventilating, which come into insulating and so on of the wall system, and also part 10, energy and water efficiency. And you'll also be influenced by municipal planners, zoning requirements, the National Fire Protection Association, NFPA requirements also. In the design phase also, you're going to be looking at the grouping or classifications of your buildings. For example, if you've ever looked at the code, Group A, Division 3 is arenas, and Group C is residential or multi-unit residential. Group B is detention centers, Division 1, Group B, detention centers. So in those areas, when you're looking at those parts of the code, they will point you to either using a non-combustible building product and material, which meets S114 or S135, or if you choose to use a combustible product, the code will direct you to 3.1.5.5. And that's the tests that we discussed, the CAN ULC S134. After you've designed and specified the material and the proper testing that the material should be going through, and you're in the construction phase, communicate with that contractor and look at those shop drawings, look at the assembly, review the material that is being used, make sure if it's a combustible type material on the wall system, it meets S134 and they have a test for S134. Better yet, if they have a listing, it is better than the test. And check the material that is it's site consistent with the shop drawings. You're getting FR core, which is a white gray core, and not a PE core of the cladding material, which is a black core. Here's a project example. Half-inch interior gypsum wallboard. You have 6-inch steel studs, exterior grade gypsum, and then the thermal spacer there is attached through the exterior grade gypsum into the stud wall. You could have 2, 3, 4 inches of mineral wool insulation. The thermal clip is there, and then the MCM cladding system. So now let's define your project example that we just looked at. Let's define it in detail. So when you're reviewing that project example and you're reviewing the shop drawings, make sure that the shop drawings conform to what has been tested or listed. Okay. Reject the design if it fails to meet the S134 assembly that you're looking at. And then look at all the additional minor combustible components, such as thermal clips and so on. If there's a significant difference or deviation from the tested assembly, then get with your code consultants, see if there's an engineering judgment that may be required to approve the wall assembly. In Ontario, we have what's known as an alternate solution in the Ontario Building Code. As we learned in past slides, combustible materials in Ontario can only be used up to 6 stories. But again, since we have an objective-based building code, you can apply to the local building officials for an alternate solution to use those materials above 6 stories. So what does the alternate solution do? It really compares the permitted area of combustible claddings in a 6-story building versus the building that's being planned and proposed. Lastly, the alternate solution kind of validates the performance of the combustible cladding with regards to testing demanded in the building codes. And really, these alternate solutions are done by fire code consultants. LRI, which is one of the best code consultants in Canada, has done a few of them with us. This slide basically says the Ontario Building Code is an objective-based code, and one path is to comply with prescriptive requirements, or the alternate solution must satisfy the intent, objective, and functional statements associated with the relevant articles in the code. And all of these alternate solutions are subject to acceptance by the chief buildings official of every city, such as Toronto or Hamilton or Markham, etc. In this segment of the presentation, I want to discuss briefly trends in wall construction and how the Energy Code is really clashing with some parts of the building code, especially life safety and fire in terms of Part 3. The Grenfell Tower example is a great example. They used polyisocyanated insulation, which is a foam, but offers great insulating value, but it burns and so the systems really have to be tested, which that one was not, with polyiso and aluminum composite panel. The other trend we're seeing is fire barriers or cavity barriers within the rain screen system. These barriers could be vertical or horizontal. The vertical barriers are found mostly in corners of the building, at building corners, and then the horizontal cavity barriers are often designed in such a way they are 2 to 3 modules in height, and then you would have a stop to stop if there was a fire, any fire propagating up the cladding. In this illustration, we show a light gauge metal used as a fire stop in the cavity, almost like a through wall type flashing. The next slide is a relatively new development, but let's run the video and we'll describe it. It is a intumescent strip fixed to the substrate, and when that strip kind of detects a rise in temperature, expanding insulation like mineral wool insulation will expand into the cavity and form a fire break. These fire stop developments will add to typical attachment systems. Some typical attachment systems here, as we discussed in the presentation, again, are, this is off a steel stud, exterior grade gypsum, the insulation panel system. This is a horizontal and vertical joint with a thermal spacer. And this is it, an actual picture of the thermal spacers being installed with the mineral wool insulation. Now, the last thing that I want to discuss in the presentation today is really to reinforce the tests for combustible and non-combustible claddings. In Canada, what you should be specifying and what you should see in your specs when specifying these materials is that the material is tested to CAN ULC S102, and that's a surface burning test which measures smoke development and flame spread. S102.2 is a test method for determining flame spread and smoke development in ceiling application and soffit applications. In fact, if you remember that picture of Ryerson Student Center, we actually had to peel the aluminum skins off the composite material and test it to S102.2 to make sure no dripping of the core occurred. CAN ULC S114, again, that's the test for determining non-combustibility in a building material. S135 is another test for determining combustibility parameters in a building material. And then S134 is the standard method for fire tests for exterior wall assemblies. Because we're so aligned and so close to the US border, and a lot of materials flow back and forth across the US border, it should be noted that the US tests are similar but not equal to Canadian tests. Mostly the Canadian tests are more severe than the US tests, but this slide just illustrates the US test and the similar but not equal to the Canadian test. And then just some pictures of the apparatus that is used to perform these tests. And this is the full-scale fire test. The Canadian test is the S134 on your left, and the NFPA 285 is the American test. Like I said before, the Canadian test is one of the most severe in the world in terms of heat output and fire output in the test. The NFPA 285 has lower values of fire output and heat output. Just some points to remember at the end of the presentation. no wall system that is tested in accordance to S134 is exactly the same as what you will be building and detailing on site. FR, when you see FR in a specification, means fire retardant, not fire resistant. It means the material is still combustible. And then non-combustible products are usually monolithic in structure and their makeup. And combustible claddings are usually made up of different types of laminate cores, like an outer skin, a core, and a back skin. So that's our presentation for today. I'd like to run a short video. What we're looking at here is solid aluminum plate on the left-hand side of the screen, and Mitsubishi Alpolic FR on the right side of the screen. I want to show you this video just to illustrate that this is an Australian test, but 3 mil solid aluminum plate under these severe tests reacts almost just as the same as Alpolic NC. On the right-hand side of the screen. See the fire propagating up the aluminum plate as well as the composite material. What's funny about this is the aluminum plate actually fails. The solid aluminum plate actually fails because the fire is so severe that it kind of melts the aluminum fastening about 17, 18 minutes into the test. You can see both materials are kind of reacting in a similar fashion, and the fire is quite severe. But these tests are run for about 30 minutes. And the reason that they're run for 30 minutes is that gives ample time for the fire department and the local municipality to get to the fire and extinguish it. So that is the end of our presentation. Thank you for attending, and I hope you enjoy the conference. Next, we're going to have a short Q&A for anyone that's interested in asking any questions. I can't say that I can answer them all, but I will certainly try, and I'll get back to you if I can't answer them. Thank you for attending again. Look forward to seeing you next year, and enjoy the rest of your conference.
Hello, my name is John Robus. With me just on audio is Edmund Wong, and thank you for attending our presentation. And if there's any questions, we can take them now.
Hi, John. First question is, how many aluminum composite material projects have been used in non-combustible construction?
Well, in terms of aluminum composite, there has been many, probably about 30 buildings in and around Toronto. Off of my top of my head, really the TIFF building that most people know of with the Daniels group, that has aluminum composite material on it. The RCMI, which is a project with Zeidler Roberts, or Zeidler Partnership now, was done 4 or 5 years ago. It's a 50-story condo and museum building. Most of the buildings that we're doing are buildings of non-combustible construction. River City is another project, but all of these buildings are of non-combustible construction, and they do use combustible cladding. I know it's a mouthful sometimes, but they do use combustible cladding on these buildings. But it's safely used with the proper systems and proper proper, that's what we're trying to get into this presentation, the proper systems, proper installations, and so on.
Okay, we have a question from the audience from Surendra. When and in what conditions zinc will be used compared to composite aluminum?
Sorry, I didn't hear that.
When and in what conditions zinc would be used compared to composite aluminum?
Zinc could be used? Is that right?
Yes.
Yes. Okay. Well, zinc, if it's natural zinc, monolithic zinc, it's considered non-combustible. But we do have metal composite materials, that is lamination layers, like the core and 2 sheets of zinc on either side of that core. They can be used in non-combustible construction also. We've just used a lot of zinc on the near the Air Canada Centre, the ICE condominiums. All of that soffit is composite zinc material. So just to repeat, if it's monolithic zinc, like let's say it's 1 millimeter thick zinc, it can be used on any building of non-combustible construction without a test. But when it comes to a metal composite material, you have to have that S134 test. Does that answer?
Our next question comes from, again, the audience, a logman. Please comment on fastening method for semi-rigid insulation out to avoid puncturing AB that is applied on sheathing.
Okay, with semi-rigid, like a mineral wool, we normally use stick pins. Stick pins are employed a lot, and also the Z-bar systems also capture that insulation from it not disengaging from the backup wall.
Our next question comes from Paul, and it is, what maximum thickness, heaviest gauge, is available in pre-painted metal, not necessarily as a composite sandwich?
Right. In the Ontario marketplace, the thickest that we've used is on the Ripley's aquarium project. It's about 3/16 aluminum plate employed on that project because of, well, our winters and the ice falling off of the CN Tower. So I believe that was about 3/16. That's about as much as you can handle on site. 4.8 millimeters.
Our next question comes from Jennifer. You made a comment that you used a piece of metal as a thermal barrier. How did this get approved from a code perspective?
A piece of metal. I guess you're referring to our thermal clip. If that's what if I made that comment, the thermal clip that we employ, that tack clip, if you saw the picture, it was solid aluminum. So that is considered non-combustible, and it's sometimes considered a minor combustible component. So if it's non-combustible, that thermal clip, it is approved.
Our next question comes from Corey. Is there any plan for manufacturers to test various wall assemblies under S134 so the tests are available?
Well, all manufacturers in our business have tested to S134. The thing to keep in mind is that no manufacturer can test every combination of wall system that is designed. What I mean by that is you may have a different thermal spacer, like a Cascadia thermal spacer or a tack clip or the T-clip. So those could be different. But the material, there is tests like some fiber cement manufacturers, for example, are not considered non-combustible. So they have to test to S134. So what I'm saying is the combination of that wall system could be a little bit different, but then you could consult with your code consultant, people like LRI, for example, and they could make an engineering judgment on that. I don't know if that's quite clear, Corey, but it is the different combinations within the wall system really can't be tested. There may be 10 different manufacturers of different minor combustible components in that wall system. And the other point that I want to make is if the manufacturer has a listing, it is better. The listing basically proves that the manufacturer tests that material every year, and that material that is produced is the same material that was tested to the S134.
Our next question is, can you please speak in a little more detail about the findings in the fire at the London Grenfell Tower some more?
Okay, well, I'm not an expert in it, but the firm that we usually deal with, the LRI, gave me that slide. But what we know is the aluminum composite material that was used on that fire had the wrong core. It wasn't a fire retardant core, and it was a polyethylene core. So that was the first kind of mistake on that building. Also, the cavity depth here in Ontario, we designed like a rain screen system to be about 1 inch of cavity depth from the mineral wool insulation to the backside of the aluminum rain screen or the aluminum composite. In that particular building, they allowed probably 4 to 6 inches of cavity depth, which allowed the fire again to propagate, and it was almost a chimney effect. Also on that building, they used just on the envelope I'm talking about, they used polyisocyanurate insulation, which is also considered combustible within our code, and it burns. And to my knowledge, no system in the Canadian code anyway has passed with polyisocyanurate insulation. So you can't have a foam insulation with a combustible cladding material such as an ACM or a phenolic type panel. It's just, well, not allowed in our code, and no system has passed yet. So those were the big things. The insulation was combustible, and that was to tell you the truth, with the energy code too, because they wanted, high R values and high U values in this retrofit. And another thing too is the inside of the building. On the inside, it was under construction. Stairways and escape routes were blocked off. There was only one to get out, unfortunately, and it wasn't a sprinklered building, as most of our high rises here in Ontario now are. But that's basically what I know about it.
Our next question comes from Constantine, and they're asking, is the thermal strip barrier approved by CCMC, and is the report and what is the report number?
No, it's not that thermal strip barrier. It's not approved by CCMC to my knowledge yet. It's kind of a new development in the marketplace. What I was trying to show in the presentation there was kind of a new trend in construction.
Our next question comes from Ahuva. How does the A2 core on an ACM panel differ from the PE or FR core?
The A2 core is a European core. It has more mineral content in it, And I know a lot of architects and designers, we do nowadays do our research like we're doing it right now, electronically and on the web. The A2 core in Europe is considered non-combustible, and we get those questions a lot. But if I tested an A2 core here in Canada, it would still release more than 3 megajoules of energy per meter squared, and therefore it would be considered combustible here. So the A2, any A2 material out of Europe is still considered combustible here in our marketplace in Canada, and I believe in the United States also, because of the severity of our S114 test and S135 test. That being said, I know like Alpolic Materials has just released in Europe an A1 core, which we're trying to test here, which will release less energy than that. So we're trying to get a really a core that is that's considered non-combustible in our marketplace, but that testing is still going on.
Our next question comes from Natasha, and she would like to know, when was your product introduced into the Canadian market, and has the product's composition evolved at all since the introduction?
On our product from Mitsubishi, it was introduced in the Canadian market in 1992. Products like aluminum composite materials like Alucobond and Renocobond were introduced before that in the Canadian market in the early 80s. And yes, it has evolved in composition, and that's why I mentioned the listing of the material, because the alloy of aluminum could change, the ingredients in the FR or fire retardant core could change, and that's why the manufacturer should carry above a test, because a test is a test in a point in time. So above a test, they should carry a listing. So what that listing does is that UL or Intertek Warnock Hershey goes inside the Mitsubishi plant every year unannounced. They ask for a piece of FR material that is produced at that time, like 2021, for example, this year, and they will make sure that the ingredients of that panel are the same as what was tested. And that's why we carry a listing instead of a test. And a listing is more important than a test. And a building official in any city would like a listing more than a test also.
Our next question is, how long does it take to complete an alternate solution, and who bears the cost?
Right. Good question. We've done many alternate solutions in the Toronto area. As a manufacturer, we bear 50% of the cost. I've had it because of the developers like the material, the architects like the material, the client does. People like Lanterna and others have agreed to the cost. And the cost is, when you're looking at a large project, the cost is relatively small. It's about $4,000 to $5,000 for the report, and the city in Toronto anyway requires $2,000 to review the report. So I would say it's a combination. Like the quad phase 2 project was just approved at university, and the developer bared the cost because, well, the material was more cost effective than any other material that was considered.
Okay, our next question comes from Ahmad. Does OBC allow a wall assembly for a 2-story school building, A2, to be constructed by corrugated metal cladding and polyiso insulation over concrete block wall?
Yeah. I don't know I can get back to him on that. I don't know the answer to that. I'd have to speak to our code consultant with corrugated and foam plastic insulation. I don't think it would be a problem just because it's 2-story, and like 24 to 26, 27 feet. The maximum in the code where the cutoff is for any type of foam insulation, to my knowledge, is about 60 feet, like I said, in Ontario, where you have to present an alternate solution and so on. But I could get back to him on that.
And Sasa would like to know, explain please the listing versus testing difference in light of concurrency just mentioned.
I'm sorry, can you repeat that? Sorry.
If you could explain the listing versus testing difference in the light of concurrency.
Okay.
Referring to the previous question.
Right. So, like I said, the listing is, so when we list, for example, a CAN ULC S134 on our material, or an S102 on our material, we give the testing agency, the third party, 6 samples and so on. They not only test it for fire, but they examine the materials, so the alloys, the composition of the core, and so on. So they actually list that material, and they make sure that when we run these tests, and we run new tests, not every year, but maybe every 3 or 4 years, that we would run a new test. We run it actually every time we change the composition of the material. I don't know if that explains it, but the listing is basically the material is checked yearly, while a test is a test in a given point of time, let's say 2018. By 2021, the composition of that material or the formulation could have changed. We would have to retest again.
Okay, and Ryan would like to know, is there even a need for combustible cladding materials?
Well, yes, I believe there is, because you can only do so much in design with monolithic materials. Like I said, monolithic materials, are heavy. The composite materials or combustible materials are lighter weight. Insulated foam panels, for every inch of foam, you get 6 to 7 units of R. To achieve that, sometimes with a wall construction, you may need, a thicker wall construction, a very thick wall construction. So as long as we're doing it safely, we're doing it per the code, we're using the proper type of for insulations. Yes, I think this is a viable material, and believe me, there's been, I know the life safety implications, but there's been, well, hundreds of millions of square feet installed in Canada, and in the United States, and billions across the world. So it is a flexible local solution.
Thank you, John. And that was our final question.
Okay. Thank you very much for attending. It was great. And everybody stay safe and stay well.